Hello and welcome to this video presentation on data augmentation for deep learning modeling of composite materials. This work was done by our research group at the University of Gothenburg with contribution from myself and my colleagues Hon Lam Chung and Mohsen Mirkalov. In this study, we explore a method to increase a scarce dataset for training of deep learning models. So when we're working with artificial neural networks as surrogate for material models, we typically start with a 3D micromechanical model of a representative volume element, or an RVE. Then we want the neural network model to predict the homogenized material response. In other words, what is the average output of a simulation? So in this study, we're interested in how this response would change if we would alter the coordinate systems of our RVEs using a rotation tensor. And this approach allows us to complement our original data of material behavior across different orientations without doing additional simulations and thus saving significant time and resources. To give you an idea of the impact of this method, using our approach, our model accuracy increased from 93% to 96% in random loading cases, and it went from 80% to 94% accuracy in specific loading cases. Now, in this video, I'll go through the process of data augmentation of 3D material models and the advantages of using this approach. Now, this study focuses on short fiber reinforced composites, or SFRCs. Now, short fiber composites are essential in various industries such as aerospace, automotive, and civil engineering. But what are the advantages of using short fiber composites? Well, they have a high strength to stiffness, strength to weight ratios, and are therefore suitable for lightweight applications. But more importantly, they're also cost effective to manufacture and can be used in injection molding processes. And one can therefore take complex 3D parts and manufacture them using a mold, so they can easily be mass produced. Now, traditionally, short fiber composites uses high-fidelity numerical simulations like finite element analysis or fast Fourier transfer form to simulate the response of an RVE under different loading conditions. However, these simulations are computationally expensive and time-consuming. So an alternative approach is to use recurrent neural networks to approximate the function of material response under these loading conditions. And this needs to be recurrent since there's a history of the plastic deformations in the material, and the disadvantages of using an RNN as a surrogate model is that they are data hungry, requiring extensive data sets for accurate training. Now, in order to address this problem, we propose using data augmentation. So to validate the data augmentation approach, we start with a unidirectional RVE as our reference, and then by rotating the fiber orientation 90 degrees, we can generate a new RVE, and then we use the same input for these simulations with the same strain paths, but for the bottom case, we also apply a 90-degree rotation tensor to this strain path. We then rotate back the output stress of these simulations to the configuration of the reference RVE. Then we can compare the outputs of the original and the rotated simulations, and we observe that they yield the same mechanical behavior, confirming that our data augmentation process preserves the material response, and that this consistency is crucial, as it ensures that our augmented dataset is reliable as original data. Now, there are small differences in the output paths here, which is due to the stochastic stacking algorithm of the fibers. Now, to generalize this process for any fiber orientation, we focus on rotating our dataset using a rotation tensor to rotate the orientation tensor, which contains the probability of the orientation of the fibers and the strain input as well as the strain output of an RVE simulation. So by starting with these tensors, we apply a random rotation tensor to create a new version of the data. To generalize a random rotation tensor, to generate a random rotation tensor M, we utilize the Arvos algorithm. Now, this rotation process enables us to simulate different fiber orientations without additional FE analysis and significantly expands our data set. Then the next step is to train our recurrent neural network on this augmented dataset. So our model architecture consists of 3 gated recurrent unit GRU layers, which each containing 500 hidden states designed to process sequential data efficiently. So here's a breakdown of the model inputs and outputs. So the inputs are 13 features, including 6 unique orientation tensor components and 6 strain tensor components, and a fiber volume fraction. Now, the architecture, as explained, 3 hidden layers with each GRU layers, each consisting of 500 hidden states, followed by a dropout layer with a 50% dropout. The output layer has 6 neurons, each corresponding to a unique component of the stress tensor. So now the model was trained on the 547 samples of original data. Then each sample was augmented through a rotation ranging from R0, which contains 0 augmented simulations, and then up to R20, which contains 20 rotation matrices, and thereby our data set is expanded 20 times since each rotation is applied to each simulation, therefore creating a diverse data set, and significantly enhances the model's training. So for more information on the training specifically, you can check out our previous video on RNN training, which also includes transfer learning. We won't be covering more of that today. Then moving on to the results of the study. So here we see that adding random rotations increases the model's accuracy. So by progressively increasing the number of random rotations from R0 with only the original data to R20, which is 20 times as large of a data set, has 20 rotation matrices, we observe a clear decrease in our error metrics. Now on the left-hand side you see a bar chart of this, and now to test on the test data set, and on the right here you can see an example plot of the stretch predictions comparing the accuracy of R0, R3 and R20, while the target is the simulation target. Furthermore, we also tested this RNN on specific loading cases of various types of cyclic loading, and we observe a clear decrease in the error metrics. So on the left-hand side here, you see a bar chart again showing how the error decreases as we go from R0 to R20. And on the right-hand side here, we also have a plot of uniaxial loading of sigma 1,1 versus showing stress versus strain predictions, and we compare the R0, R3, and R15, and this improved accuracy of stress predictions demonstrates how effective data augmentation is in enhancing our model's performance, allowing it to generalize better across various configurations. So in summary, our data augmentation method provides a practical solution to data scarcity problem in deep learning model of composites. So by randomly applying random rotations to our input data, we can expand our dataset significantly. So thank you for your attention. For more information about our work, you can check out our lab's website at materialslabs.org. Thank you.